In the previous video, we saw that when the substrate has multiple beta carbons, an E2 mechanism can give you more than one product, different products for different beta carbons. But that raises the question, which beta carbon would give you the major E2 product and which would give you the minor E2 product? Well, that's an issue that we're going to discuss in this video. In this video, we're going to focus on finding the major E2 product for a straight chain molecule because an E2 reaction that's carried out on a ring raises additional issues that we'll have to talk about in a later video. So our goal for this video is to discuss which beta carbon would give you the major E2 product on a straight chain. What type of functional group is this? It's an alkene. What type of functional group is this? It's an alkene. How about this? An alkene. I hope you can see these are all alkenes. They all have carbon-carbon double bonds. Now this is what's called a monosubstituted alkene. It's called monosubstituted because it's attached to one carbon chain. Mono is a prefix that means one. Can you guess what this would be called? This is called a disubstituted alkene. This is called disubstituted because it's attached to two carbon chains. Di is a prefix that means two. What do you think you would call this? Well, that one is another disubstituted alkene. Again, it's attached to two carbon chains. What do you think you would call this? That one's another disubstituted alkene. Again, it's attached to two carbon chains. What would you call this? This is a trisubstituted alkene because it's attached to three carbon chains. Tri is a prefix that means three. What would you call this? This is a tetrasubstituted alkene. Tetra is a prefix that means four, and this alkene is attached to four carbon chains. Now, the important idea we have to memorize is that substitution with carbon chains stabilizes alkenes. Nature likes it, so to speak, when alkenes are more substituted with carbon chains. So which of these would be the most preferred? Tetrasubstituted would be the most preferred, then trisubstituted, then disubstituted. Monosubstituted alkenes would be the least preferred. Why? Why does substitution with carbon chains stabilize alkenes? Well, for simplicity, I'm not going to get into that. If you're interested, you can find an explanation in your textbook. But we are just going to memorize. We'll just memorize that substitution with carbon chains stabilizes alkenes. Notice you have to say that substitution with carbon chains stabilizes alkenes. So substitution with carbon chains doesn't necessarily stabilize other molecules. We're just learning here that it stabilizes alkenes. So don't just say substitution is good. Don't just say substitution is good. It might be good in some situations and bad in other situations. You have to say that substitution with carbon chains is good for stabilizing alkenes. Substitution with carbon chains might very well destabilize other types of molecules. Oops, I can see a little typo there. I meant to say here that this was substitution with carbon chains. Substitution with carbon chains stabilizes alkenes. By the way, you should already know also that substitution with carbon chains also stabilizes carbocations. You should have already learned, for example, that tertiary carbocations are the most stable because they're the most substituted with carbon chains. This is an idea that I talked about in my series on SN1, and this is an idea that I also explained in the SN1 series. I explained why substitution with carbon chains stabilizes carbocations. That's not directly relevant for E2 reactions, but as long as we're learning this idea, we might as well also review this idea. So again, don't just say substitution is good. It's good in some situations and bad in other situations. You should say that substitution with carbon chains is good for alkenes, and substitution with carbon chains is also good for carbocations, but there might very well be other situations where substitution with carbon chains might be destabilizing. Well, remember that our goal in this video is to determine which beta carbon gives the major E2 product. So now would be a good time to try to use what we just learned to answer that question. So I encourage you to pause the video and you use what we just learned about substitution. How could this help us to decide which beta carbon would give you the major E2 product? Well, here's the answer. Here's the rule. The major product for E2 comes from using the more substituted beta carbon. Can you explain why that is? Well, remember, substitution with carbon chains stabilizes alkenes. It should make sense to you that if you use the more substituted beta carbon for E2, that will produce a more substituted alkene, and therefore a more stabilized alkene. On the other hand, if you used a less substituted beta carbon for E2, that would give you a less substituted alkene. That would produce a less substituted alkene, which would be a less stabilized, less preferred alkene. So since we prefer to make a more substituted alkene, it makes sense that E2 prefers to occur at the more substituted beta carbon. Now let's make some additional comments. First of all, it turns out that the way you think about E2 reactions for a straight chain molecule is somewhat different from the way that you think about E2 reactions for a ring. So in this video, I'm going to be focusing on how to think about E2 for a straight chain. And in a later video in this series, we'll start talking about how to think about E2 for a ring. Next point, notice that even though this video series is focusing on E2 reactions, this rule also works for E1 reactions. E1 reactions also produce alkenes, and therefore E1 reactions also prefer to use the more substituted beta carbon so that you can make the more substituted, more stabilized alkene. So this is a rule that generally works both for E2 and for E1 reactions. Next point, this is called the Zaitsev rule. It might be helpful for you to know that this is called the Zaitsev rule. And next point, almost every rule in organic chemistry has an exception. The Zaitsev rule has an exception. If you carry out an E2 with tert butyl oxide, the pattern reverses, and the major product for an E2 with tert butyl oxide would use the less substituted beta carbon. Pause the video and see if you can figure out a reason for that. Remember, this is the structure for tert butyl oxide. Pause the video and see if you can think of a reason why tert butyl oxide would prefer to attack the less substituted beta carbon rather than the more substituted beta carbon. Here's the answer. Because this carbon is tertiary, there is a lot of steric hindrance in this molecule. This carbon is surrounded, this O- is close to 3 methyl groups, and any of those methyl groups could get in the way of the O- attacking the beta carbon. This base can get in its own way, so to speak. This methyl group could get in the way and block the O- from attacking the beta carbon. Or this methyl group could get in the way and block the O- from attacking the beta carbon. Or this methyl group could rotate to get in the way and block the O- from attacking the beta carbon. So since there's so much self-created steric hindrance from this base, it's easier for tert butyl oxide to attack the less substituted beta carbon because the less substituted beta carbon will have less steric hindrance. It's easier for tert butyl oxide to attack the less substituted beta carbon because the less substituted beta carbon is surrounded by fewer carbon chains and will therefore have less steric hindrance. The tert butyl oxide is already creating a lot of steric hindrance on its own. It can't, it will be really slowed down if there's also a lot of steric hindrance around the beta carbon. Notice that this pattern is called the Hofmann rule. Now would be a good time to pause the video and memorize this rule and this exception. The major product for E2 and E1 uses the more substituted beta carbon because that produces a more substituted, more stabilized alkene. But an exception is that tert-butyl oxide prefers the less substituted beta carbon because the less substituted beta carbon has less steric hindrance. By the way, notice that this says the major product, not the only product. So E2 can attack multiple beta carbons. We're not saying that E2, so in the Zaitsev rule, we're not saying that E2 can't attack the less substituted beta carbon. We're just saying that the less substituted beta carbon would be the minor product, and the more substituted beta carbon would be the major product. This rule tells you which beta carbon gives you the major product. We can also attack the other beta carbon. That would just be a minor product. By the way, remember that this is the bond line notation for tert-butyl oxide, and this is the condensed notation for tert-butyl oxide. You won't know when to use this exception unless you can recognize when you're looking at tert-butyl oxide. Make sure you can recognize the structure of tert-butyl oxide in bond line notation and in condensed notation. I hope you can convince yourself that these two structures are the same structure. In cases, we have one carbon attached to 3 methyl groups. One carbon attached to 3 methyl groups. This carbon is tertiary. That's where the tert in the name tert-butyl oxide comes from. Please pause the video and try this problem. I hope you actually tried that. Now let's go through it together. We could start by numbering all the carbons, including this one. Now we notice the ionic bond, and we draw in the formal charges for that ionic bond. We can identify some roles. We expect O- to be a nucleophile or a base. Neutral bromine will be a leaving group, and therefore carbon 2 is our alpha carbon. And we can see that we have a tertiary alpha carbon because carbon 2 is attached to 3 carbon chains, carbon 3, carbon 1, and carbon 4. Don't assume the mechanism is E2. Use the table to determine the mechanism. Tertiary alpha carbon puts us in the bottom row of the table. O- puts us in the right-hand column of the table. And the table predicts an E2 mechanism. Make sure you write down the name of the mechanism. Now we can continue assigning roles. Now we expect O- to be a base, not a nucleophile for an E2 reaction, and we know O- is a strong base. We should label the alpha and now the beta carbons. So we have a bunch of possible beta carbons here. Carbon 3 is a possible beta carbon. Carbon 1 is a possible beta carbon. And carbon 4 is also a possible beta carbon. Now the problem asked us not for all the products, but just for the major product. So we have to decide which of those beta carbons will give us the major product. Well, we can use the rule that we just learned. The major product comes from using the more substituted beta carbon, and carbon 4 is more substituted. To make that clear, notice that carbon 4 is a secondary beta carbon. Carbon 4 is secondary, attached to 2 carbon chains, carbon 2 and carbon 5. Carbon 3 is a primary beta carbon, attached to just 1 carbon chain, carbon 2. And carbon 1 is also primary. While a secondary beta carbon is more substituted than a primary beta carbon, so we've determined that following this rule, we should use carbon 4, the more substituted secondary beta carbon, for our major product. So the best thing I think to do now is to erase this beta and this beta so that we are indicating that this is the beta carbon that we're actually using to avoid confusion. Now we can draw the mechanism. The electrons should move away from the base, the electron donor, towards the beta hydrogen. Another arrow to show the pi bond forming between alpha and beta carbons. We take these electrons to make a pi bond between the alpha and beta carbons. By the way, we can also mention now that we're using carbon 4 as our weak acid, because this is the carbon that's giving up the hydrogen. And one last arrow to show the leaving group leaving the alpha carbon. Now we can draw the product. This arrow tells us to form a bond between the oxygen and this hydrogen. And we change the charge on the oxygen from negative to neutral because it lost electrons. This arrow tells us to form a pi bond between carbon 2 and carbon 4. Here's that new pi bond between carbon 2 and carbon 4. This arrow tells us to break the bond between carbon 2 and the bromine. Break the bond between carbon 2 and the bromine. The bromine started neutral and gained electrons, so it should end up with a negative formal charge. By the way, notice this problem didn't actually tell us to draw the mechanism. So you can get full credit on this problem if you just get the correct product. You don't have to draw the mechanism. Nevertheless, I strongly encourage you to draw the mechanism, because the mechanism is your tool for figuring out the correct product. So as a beginning OChem student, you should usually draw the mechanism even if the problem doesn't require you to draw the mechanism, because the mechanism is your tool for thinking about and understanding the problem and for figuring out what the product will look like. This might be a full credit answer, but it's not a very satisfactory answer because remember, carbon 2 here, this alkene carbon should be trigonal planar. And remember that the bond angle when something is trigonal planar should be 120 degrees, which means that this angle should equal this angle, which should equal this angle. But obviously we haven't drawn it that way. These angles are not all equal. So it would be best to adjust the bond angles so that they're actually closer to 120 degrees. So this is a much better way to show the trigonal planar geometry around carbon 2. Do you see now all these bond angles are approximately equal? They're all approximately 120 degrees. That's a much better way to show the alkene. I also think it's really quite helpful here that we're numbering all the carbons. By numbering all the carbons, we're much less likely to accidentally add or drop a carbon in this product. If you don't number all these carbons, it would be very easy to accidentally add or drop a carbon when you draw the product. Remember, your numbers should be consistent with the starting material. It would be useless to call this carbon 8. You need to call this carbon 1 to be consistent with how it's numbered over here. For these types of instructions, the product that the professor probably cares about is this one. So if there was a box, this would be the answer that I would put in the box. It's good to draw these products for your own understanding because they were produced from the mechanism. But if there's a box, the answer that we would put in the box would probably be this one. This is probably the product the professor cares about here. It's important here that the problem asked for the major product. If the problem had just said draw the products, if it just said draw the products, then you would want to show the attack both on carbon 4 and on carbon 3. If they just say draw the products, you'd have to show the product from attacking the more substituted and the less substituted beta carbon. But since the problem just says draw the major product, we knew just to draw this product. So read the instructions carefully. So this problem gave us some practice with drawing the major product for E2. The usual rule for the major product for E2 is to use the more substituted beta carbon. And remember, again, it's really helpful that we're labeling the alpha and the beta carbons so that we can think clearly about them on these problems. Please pause the video and try this problem. I hope you did try the problem. You'll get a lot more out of these videos if you actually try the problems on paper. Let's start by numbering the carbons. These carbons in the parentheses are difficult to number, so I won't number them. I'll just number this carbon. Now we notice an ionic bond, which allows us to put in formal charges on the oxygen and the sodium. Make sure you actually write down the formal charges for ionic bonds, because formal charges are the most important factor in organic chemistry. So we can identify that this oxygen will be a nucleophile or a base. Neutral bromine will be our leaving group. Carbon 2 will be the alpha carbon. It's a tertiary alpha carbon. So our table again predicts that the mechanism will be E2. So we have to identify the beta carbon that we're going to use. Again, there's 3 beta carbons. Carbon 3, carbon 1, and carbon 4 are all beta carbons. We have to decide which one to use. We're not going to use all of them because the problem asked for the major product. We have to decide which is the more and less substituted beta carbon. Well, carbon 3 is a primary beta carbon. Carbon 1 is another primary beta carbon, and carbon 4 is a secondary beta carbon. Now, our normal rule would be to use the more substituted beta carbon. But did you recognize that in this case we have to apply the exception? Remember, there's an exception that applies when you're using tert butyl oxide. Well, I hope that you recognized this is the condensed notation for tert butyl oxide. The condensed notation for tert butyl oxide. Here we have a tertiary carbon attached to 3 methyl groups. And the O-, that's the structure of tert butyl oxide. So in this exception, we should be using the less substituted beta carbon. Remember that tert butyl oxide prefers to attack the less substituted beta carbon because that would have less steric hindrance. Tert butyl oxide is so bulky that this is what's called a bulky base. It's so bulky, such a bulky base, that it provides a lot of steric hindrance that kind of gets in its own way and prevents and hinders it from attacking the beta carbon. So it's a lot easier to attack a beta carbon that has less steric hindrance, a less substituted beta carbon. But which beta carbon should we use here, carbon 3 or carbon 1? We're not going to use carbon 4 because that's the more substituted beta carbon. But carbon 3 and carbon 1 are both primary, so which one should we use? Or should we use both? Should we draw 2 products from attacking both of them? Well, I hope that you can see that it doesn't matter which of these beta carbons you use because they will both give you the same product. You can see that because carbon 1 and carbon 3 both have the same connectivity. Connectivity is a technical term that refers to the complete series of all the atoms that an atom is connected to and all the atoms that those atoms are connected to, etc., for the entire length of the molecule. Well, it should be easy to see that the connectivity of carbon 3 is the same as the connectivity of carbon 1. Carbon 3 is directly attached to 3 hydrogens and the alpha carbon. That's its connectivity. And carbon 1 is directly attached to 3 hidden hydrogens and the alpha carbon. That's the same connectivity as carbon 3. Since carbon 1 and carbon 3 have the same connectivity, we know that they're going to result in the same E2 product. There is an exception to that rule when there are stereocenters, but this molecule doesn't have any stereocenters, so that exception is not going to apply. Since the 2 beta carbons have the same connectivity, we can trust that they will result in the same E2 product. That means that we can use either carbon 1 as our beta carbon or carbon 3 as our beta carbon, but we shouldn't use both of them because that would give us duplicate, redundant products. I'm going to choose to use carbon 3 as the beta carbon, so I will erase the beta label from carbon 1. I'll use carbon 3 as the beta carbon. That means that carbon 3 will be used as our weak acid. We can draw our electron pushing arrows. I'll have to draw in one of the hydrogens on carbon 3. And now I show the arrow for the base taking the beta hydrogen. Now I show the arrow for the pi bond forming between alpha and beta carbons. Now I show the arrow for the leaving group leaving the alpha carbon. Make sure you've labeled the alpha and the beta carbon that you're using. Now we draw the product. This arrow tells us to draw a bond between the oxygen and the hydrogen. The oxygen started negative and lost electrons, so the oxygen becomes neutral. This arrow tells us to erase the bond between carbon 3 and the hydrogen and to draw a new pi bond between carbon 3 and carbon 2. Here's the new pi bond between carbon 3 and carbon 2. This arrow tells us to erase the bond between carbon 2 and the bromine. The bromine started neutral and gained electrons, so the bromine ends up with a new negative formal charge. This might be a full credit answer, but it would be better to show the bond angles more accurately here. Remember that for a trigonal planar alkene, we would like all these bond angles to be equal. Well, they're very far from equal here, so let's redraw this with equal bond angles. Here's a better picture where the bond angles are closer to equal 120-degree bond angles. Again, I think it helps to put in numbers to make sure you're not accidentally adding or dropping carbons. Here's the product the professor would probably care about for this problem. I hope you can see that if we had used carbon 1 as the beta carbon, we would have gotten the same product. But if you're not confident of that, you could just draw that mechanism separately and convince yourself that that gives you the same product as we get when we attack carbon 3. So the purpose of this problem was to practice which beta carbon to attack with tert butyl oxide. With tert butyl oxide, the major product comes from attacking the less substituted beta carbon. Now, that doesn't mean that you can't also attack carbon 4. If they'd asked us for all the products, we could also attack carbon 4. But this problem only asked for the major product, and for the major product, we only attack the less substituted beta carbon. So we're continuing to use the idea of labeling alpha and beta carbons, and we used this idea. When beta carbons have the same connectivity, they result in the same E2 product. And generally, you don't want to include multiple copies of the same product in your answer. So we only have to show the product from carbon 3 here. We don't also have to show the product from carbon 1 because they're the same product. Usually the major product for E2 comes from using the more substituted beta carbon, but with tert butyl oxide there's an exception, and we use the less substituted beta carbon. Notice therefore that you have to be on the watch for tert butyl oxide. You have to notice when the starting materials involve tert butyl oxide, because that can sometimes influence the outcome for an E2 reaction. By the way, after I recorded this video, I noticed that I had missed a minor detail. I should have noticed that after we decided that the mechanism was E2, I should have updated my label here to show that we know that for E2, we're going to use the O- as a base, not a nucleophile. So I'll do that now. In fact, we know that O- is a strong base, so I should have labeled that role that the O- is playing in the E2 mechanism. You will make fewer mistakes, and you will develop your O-Chem mastery more quickly if you make an effort to always correctly label the precise roles that atoms are playing in your mechanisms. That's a really helpful habit for a beginning O-Chem student. So now you can compare these two problems. Notice that in these two problems, this starting material was the same in both cases, but we got different major products because here we were using an ordinary base and here we were using tert butyl oxide, which is a bulky base. Notice that in this case, we ended up with a tri-substituted alkene because we attacked the more substituted beta carbon. Whereas in this case, we ended up with a di-substituted alkene because we attacked the less substituted beta carbon. Here we preferred to attack the more substituted beta carbon. That gave us a more substituted alkene, and that is preferred as the major product because substitution stabilizes alkenes. On the other hand, in this case, we produced the less substituted alkene, even though that is less stable because of steric hindrance issues. You can see that attacking the more substituted beta carbon really would give you a more substituted alkene, and attacking a less substituted beta carbon really does give you a less substituted alkene. That's the basis for this rule. Remember to read the instructions carefully. This problem said draw the major product, so we drew one product from attacking one beta carbon. This problem said draw the major product, so we drew one product from attacking one beta carbon. But do you remember this problem from the previous video? Remember this problem from the previous video? This problem said draw the products. Since the problem said draw the products, we drew multiple products from attacking multiple beta carbons. In this case, we drew the products from attacking this beta carbon and this beta carbon and this beta carbon because the instructions just said draw the products. Notice that this is tert butyl oxide. This is tert butyl oxide, so we know that the major product here, the major product with tert butyl oxide, would come from attacking the least substituted beta carbon. These would be minor products, but we still include them if the problem just says draw the products. Please pause the video and try this problem. Now let's discuss. Well, to begin with, it's important for this type of problem to identify the functional group that we're dealing with. All of these molecules have the same functional group, and actually the problem identified the functional group for us. The problem reminded us that these are all alkenes because they all contain carbon-carbon double bonds. So you should ask yourself, have I learned anything about judging the stability of alkenes? And we did learn a rule for that at the beginning of this video. At the beginning of this video, we learned that substitution with carbon chains stabilizes alkenes. So we need to count how many carbon chains each of these alkenes is substituted with. This one would be monosubstituted, because this alkene is attached to one carbon chain. If you haven't done so already, now would be a good time to pause the video and write down the extent of substitution for each of these alkenes. Well, this one is tetra-substituted. Tetra means 4. This alkene is substituted with 4 carbon chains. This is di-substituted. This alkene is substituted with 2 carbon chains. This is tri-substituted because it's substituted with 3 carbon chains. And this one we could say is just not substituted. You could say it's substituted with 0 carbon chains, or you could just say it's not substituted. Well, remember, substitution stabilizes alkenes. So the least stable would be the least substituted. This is the least stable because it is the least substituted with 0 carbon chains. Then this one is substituted with 1 carbon chain. This one is substituted with 2 carbon chains. This one is substituted with 3 carbon chains. And this alkene would be the most stable because it's substituted with the most carbon chains. So now we've ranked these in order of increasing stability, from the least stable, number 1, up to the most stable, number 5. On this type of problem, it's easy to get confused and put the ordering in the wrong direction. So make sure you're clear here that number 1 goes with the least stable and number 5 goes with the most stable. We should probably make a note to ourselves. We should make a note to ourselves that the molecule with the least substitution is the least stable, which goes with the number 1, and the molecule with the most substitution is the most stable, which goes with the number 5. For these types of ranking problems, it's easy to make careless mistakes, and the way to avoid careless mistakes is writing down notes to yourself like this so that you can see the associations between concepts. Now, why did we practice this problem? Well, first of all, this is a type of problem that you might see on your exam, so it's worth practicing. But why are we practicing this problem in this video? The purpose of this video is to cover E2 mechanisms. We didn't directly deal with an E2 mechanism here, so I have a question for you. Pause the video and answer, how is this problem relevant to an E2 mechanism? How is this problem relevant to understanding E2 mechanisms? Well, here's the answer. We already discussed this earlier. We used the idea here that substitution with carbon chains stabilizes alkenes. And that's the justification for our Zaitsev rule. The Zaitsev rule says that the major product for E2 and also for E1 uses the more substituted beta carbon. And this is the justification for that. When you're doing an E2 reaction, we prefer to use the more substituted beta carbon because that will produce the more substituted alkene. And when we're doing E2, it's less preferred to use a less substituted beta carbon because that would produce a less substituted alkene. So the idea that substitution with carbon chains stabilizes alkenes is the justification for the Zaitsev rule. That's how this idea is relevant to E2 mechanisms. On the other hand, you should remember that there is an exception to the Zaitsev rule, which is the Hofmann rule. If you use tert butyl oxide, the major product would use the less substituted beta carbon. Do you remember why that is? That's for stereochemistry reasons. Tert butyl oxide is an especially bulky base that experiences a lot of stereochemistry. So that very bulky base will have an easier time attacking a less substituted beta carbon. If the base is providing a lot of stereochemistry, it's easier for it to attack the beta carbon that is surrounded by less stereochemistry. Let me remind you again of what I said earlier in the video. Don't be lazy. Don't just say substitution good. You can't just say substitution good because substitution isn't necessarily good for all reactions or for all functional groups or for all molecules. You need to be more specific and say substitution is good for alkenes. Substitution stabilizes alkenes. Substitution might well be bad for in other situations or destabilize other molecules. Don't just say substitution good. Say substitution is good for stabilizes alkenes. In this video, we discussed how to determine the major product when there's more than one beta carbon that can be attacked. We learned these two rules, the Zaitsev rule and the Hofmann rule, and we learned how to apply them to straight chains. Now, the Zaitsev rule and Hofmann rule also apply to rings. These same two rules apply to rings, but there are additional complications when you deal with rings. So because of those additional complications, we haven't given any examples for rings yet. In a later video in the series, we'll begin showing how to apply these rules to rings, where, as I said, there are some additional complications. But we're not ready for that yet. For the time being, we're going to have to continue working with straight chains. In the next video in this series, we will continue to work with straight chain molecules and E2 mechanisms, and we will see another complication. In the next video, we'll see another complication that can arise when you're applying E2 mechanisms to a straight chain molecule. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen, or by using the link in the video description box. Thank you.